All right, it's time for some practice questions. I have not yet tried these out. I just wrote all the questions, so I hope I don't mess any up. So we're going to start off with the... Shoot, I better get out my equations. So, all right, here are my equations, and I'm going to be able to refer to those if I need to. What's the highest possible water potential? And so we're talking about the solvent potential because the overall water potential might have some sort of pressure involved. We're just talking about solvent potential here. So just to recap, psi s is equal to negative I times C times R times T. Don't die on me now. Okay. And you can see here, since it's negative, if we put any values in here that are big numbers, it's just going to get our negative value to be more and more negative. So the way to get the highest value, if all values have to be negative, remember we can't make the R value negative, it's a constant. We can't make concentration negative because the lowest concentration is 0. We can't make temperature negative because it's in kelvins. So the closest way we can get to having a high number with this is to put in a 1 for our I value, our ionization, or we could go with I suppose we could go with a 0 here or a 0 here. 0 in this one would indicate that it's distilled water, which would do the same thing for this one. 0 concentration. It doesn't matter what happens to the R and the T because 0 times 0. So the highest possible water potential is 0. And let's see. Oh, I should have checked out my my units on this. So this one is just a value. This would be moles. R. Oh shoot! I'm gonna have to go back to my cheat sheet. R is liters times bars over moles times kelvins. So liters times bar over moles times Kelvin. Shoot, I got a lot of stuff there. Okay, times kelvins, and this is moles per liter. All right, I think we're in good shape there. Cancel these units. Moles and liters cancel. Kelvins cancel. My unit for the water potential is going to be in bar. All right, so 0 bar is the highest possible water potential. If you did this in a different unit of pressure, then you would have a different value. Remember, this makes sense because we're going to take the solvent potential and add it, solute potential, and we're going to add it to the pressure potential to get your overall. So if there is a pressure potential, you could add it to that 0, and that would be your way to get as high as you can go. All right, let's see if we can do the next one without stumbling so bad. How does a turgid cell's molarity compare with the molarity of the solution it is in? Turgid cell is one that has it's firm or hard, and that's because water has been going into it. So for water to be going into that cell, what has to be happening? What's going to happen to the size of this cell if water goes in? It's going to get bigger. It's going to expand. It's going to become turgid. So we're talking about a hypotonic solution. All right, so we just got to go back to our concept of what hypotonic is. And hypotonic is when we've got a lot of stuff on the inside, not a lot on the outside as far as solute, and the water goes inside. It's moving from a high potential energy to a low potential energy. So that water is going to move from high to low potential energy. Okay, so we've got that one. How does the molarity of the turgid cell compare with the molarity of the solution it's in? It must be higher. My pen is dying on me. Ooh, shoot. how does a flaccid cell, remember flaccid's going to be the exact opposite, how does a flaccid cell compare with the molarity of the solution it's in? This one's going to be a little bit trickier. All right, so there's our cell. There's the solution. What made it flaccid? Well, the water went out, right? But we don't know, in this case, if the water is still in the process of moving out or if it has reached equilibrium. So I'm going to say the molarity of the flaccid cell should be not higher, should be lower. So should have a lot of particles, a higher concentration outside the cell. It's got to be a hypertonic. And how does the molarity of the solution, how does the molarity compare with the molarity of the solution? In this case, the molarity of the cell is lower. But because eventually it could shrink enough that the cell becomes to the same concentration, I'm going to put lower or eventually equal. Ooh, 3 equal sign. All right, so lower or eventually equal is a possibility. All right. 4, application question. Had this, unfortunately, twice this month already. Your throat/tonsils are sore and swollen. Should you gargle plain water or salt water, and why? Well, they're swollen. That's part of the problem. Stuff is uncomfortable to swallow and breathe. We need to get those cells not swollen anymore. Adding more fluid to those cells is going to make the problem only worse. So what do we need to do? We need to put it in one where water is going to go in or water is going to go out. We need to put it in a hypertonic solution. To get a hypertonic solution, we would have to have more salt on the outside of our cells than there is on the inside. In this case, salt water is the good choice. And I'm going to put hypertonic. I'm not going to have that pen anymore. My kid stole all my pens. Hypertonic. And we want to take water out and shrink the cells. All right. Number 5, dehydrated people are administered intravenous, they call this IV, saline. And the saline comes from the word salt. It's actually 0.9% sodium chloride solution. If you're curious on the molarity of it, because I know chemistry gurus out there love this, it's 154 millimolar or 0.154 molar NaCl in their water. So why and what is the significance of this value? Why not just give them 100% water in their IV? I mean, they are dehydrated, so we could get them hydrated better if we gave them 100% water, right? Well, no. You remember that video of what happened when we put animal cells in distilled water? We did it with plant cells and they got swollen. We do it with animal cells and they don't have a cell wall. You get the hippo cell, and eventually it gets too big for the cell membrane and the cell breaks. Oops, I shouldn't show arrows going out because that makes it look like the cell is going to go. The cell dies because it explodes. And yeah, this can happen. So you don't put straight water into somebody. If you have contact lenses, you have a particular saline solution. It's not the same as your blood is. It's the same as the concentration of salt in your eyes. And if you were to take out your contacts and put them in a regular saline solution, and then put them back into your eyes, you'd notice a painful burning sensation. You'd notice the exact opposite if you put them in a distilled water solution and then put them back into your eyes. You would have a painful result there. So what is the significance of this value? Why do we have this 0.9% sodium chloride? It's because it's isotonic with your body. So it's going to make sure that your your red blood cells don't shrivel up and die, and they don't hippo style explode when they go into your bloodstream. All right, I'm going to do one more page, I think, of problems on the next video.